Hello and welcome to the OpenPower Summit North America 2020. My name is James Kulina. I am the Executive Director of the OpenPower Foundation. I want to say thank you for coming today. I know that we have a number of attendees from all across the globe joining in, so thank you. As well as our speakers today. I know a number of you are also coming and joining to give your talks. So I thank all of you for taking the time to let everybody know the great work you're doing. So first, a thanks to our sponsors as well, Antmicro, IBM, OpenCAPI, and Yadro. Without your support, we wouldn't be able to put on these events and let everybody know all the great work that's going on. So my name is James Kulina. I'm actually the new executive director for the foundation. I started only a few months ago. So my background is in open source. Previously, I was the co-founder of the open source cloud startup called HyperSH. We were focused on container security. We actually were the creators of the Kata Container project, which is now within the OpenStack Foundation. We worked extensively with the CNCF here at Linux Foundation, as well as Google Kubernetes team and the Docker team. Previously, I'm a former Red Hatter, working in the product group, focusing on DevOps. And then before that, I was at AT&T, where I helped them stand up their first OpenStack telco cloud. Very excited to be here today with you, as well as very excited about all the possibilities of OpenPower moving forward. So first, I want to give a shout out to Hugh Blemmings, our former executive director. He did an excellent job in establishing the foundation for future growth. And one of the best things that happened last year was the opening of the Power ISA, which is monumental, and I think will lead to really great things in the future. We also had open reference designs released. So the first one was the microwatt, and this was really a proof of concept that really only took a couple weeks to build out, and it was really just focusing on how do you consume the Power ISA and how easy it is to consume and actually get up and running a working processor. And if you want to learn more about that, you can actually attend their talk today. It's in the track 1 at 3:30. We also, just a few months ago, IBM contributed the A2I core, which was originally an embedded core, a high-performance embedded core that made its way into a number of supercomputers, including the Blue Gene Q. There's another technical deep dive into that core, and they have a talk today at 1:20. The other great thing that happened last year in 2019 was moving the OpenPower Foundation within the Linux Foundation. So we had open governance. And by joining the Linux Foundation, we really get to have access now to the best and brightest within the open source communities. We can learn about the best practices of growing a foundation and growing numbers and showcasing all the great things that you all are doing. So very excited to be part of the Linux Foundation now. So I want to talk a little bit about our vision moving forward for the foundation. So historically, the foundation was set up to really just focus on the ISA and the specification around the ISA. What I want to do, and what I'm hearing from other members, is we're really going to shift into being a more proactive foundation that energizes their member companies so they can devote engineering resources to driving a thriving ecosystem. And it's going to be around co-development of common license, free Power IP, cores, tools, software, and systems. And moving forward, we're have a lot more interaction between our members so that new innovations can occur. And part of the way that we're going to do this and to accelerate this is we're going to retool and rework our working group structure around use cases and industry segments. And the focus here is around making it easier for our member companies and our potential member companies to understand where they sit within the foundation and how they can actually potentially contribute and collaborate. And so showing the value very upfront about what's going on and how they can actually take part. We will also continue to have working groups around technologies, specific technologies, but these technologies tend to cut through many segments. And so they will still exist and they will still be moving forward. But these working groups will also be responsible for managing all aspects around compliance and verification and modification to the ISA if required. And again, one of the great things about being now within the Linux Foundation is the ability to have potential partnerships and collaboration with other foundations. And so OpenPower is really aiming towards driving these types of collaborations within the Linux Foundation, including with projects called Linux, the RISC-V Foundation, the CHIPS Alliance Foundation, the LF Artificial Intelligence Foundation, as well as the Networking and Edge and Automotive Group, Hyperledger and CNCF, and all the sub-projects within CNCF. And because OpenPower is a platform itself, we want to make sure that we're supporting all the great open source software out there that the Linux Foundation is producing. We're also going to be working directly with the OpenCAPI consortium as well as the OCP group. We actually have an entire track almost dedicated to OpenCAPI today. And so the goal here really is to create this short feedback loop for feature requirements that will inform our working groups moving forward. And so the goal is to generate this OpenPower reference IP, this common components that can be used within a number of verticals. But by splitting out our work groups based on segments and verticals, it makes it easy for our member companies to see, what are we working on that aligns with these different verticals, and then how can we engage? Who else is within those working groups, and what are they contributing, and how can we collaborate together? So you can see what's there and what you can reuse, so you don't have to reinvent the wheel. Moving forward, the focus areas for the foundation will be first around access to power systems. We want to make it as easy as possible for you to get access to test out either software or hardware, and making sure that it runs well on the power architecture. And so what we want to have is a centralized hub, technology hub, with a variety of different power systems and configurations, and in different geographical regions, so that you can easily gain access to the types of systems that you require. So we'll have a centralized way of getting access and requesting access, but we want to make sure that anybody who needs it can get to it. The other thing that we're looking at is standing up a training curriculum. So we have a number of academic institutions as members, and they've been asking actually for developing a curriculum around the OpenPower ISA, because now it's a fully nuts to bolts open source. It's a great platform for teaching. We also obviously want to have engaged and productive technical working groups. So I think how we're going to be changing our working group structure will lead to significantly higher throughput of technical innovations. We're going to continue on putting on events such as this, the summits, but also we're going to be looking at smaller events and more frequent events that are focused potentially on specific segments and specific technologies, and giving a voice to our different members to showcase what they're doing at those events as well. And we're going to be standing up meetups and workshops, mostly focusing on the developers and end users and use cases around that, so that we can have a lot of cross-pollination with the developer community. We're also going to be reaching out to all of you and asking what are you up to, so we can develop case studies and potential proof of concepts to demonstrate the value of OpenPower. And so how do you actually engage with the OpenPower community? Well, there's a number of ways. Obviously, being here, submitting talks, getting accepted, and showcasing what you're up to is one way. But there's also other ways. You can become a member of the foundation. You can join our work groups, contribute, and collaborate there. You can come to potential meetups. If you already have OpenPower software or hardware, you can get it certified and showcased on our website as OpenPower Ready. You can help us out in terms of marketing through our marketing committee. And the best way to engage with any of the leadership here is just to send us a note. So you can always reach me at ed@openpowerfoundation.org, or you can reach our new TSC chair, Tusham Bhavarni. You can also reach Dina, who is our marketing committee chair, as well as Gannison, who's our leading our academic initiatives. And if you have some kind of social media campaign that you're launching, or you want to get the word out about what you're up to, reach out to us. We'll be more than happy to learn about what you're doing and get it into the kind of campaigns that we're launching in terms of social media. So again, thank you for being here today. I'm very excited to be the executive director of the foundation and to lead to new heights and to learn about what you all are doing and the incredible work that you are pursuing. And enjoy the summit. So to kick off our keynotes today is going to be Michael Gielda, the Vice President of Business Development at Antmicro. So please welcome Michael.
Hello, everyone. I hope you can see me. Let me try to advance the slide here just to check if it's all working. Okay, so today I'm going to tell you a little bit about the open source ecosystem powering innovation and FPGA and ASIC development. And I couldn't help myself, and of course I capitalized the power there because of course we're at the OpenPower event. So first, why am I here? Why am I talking on behalf of my company here at this OpenPower event? I think the story about Antmicro and open source needs telling because we've been founded 11 years ago, and throughout that time, a lot of things have changed. But the one thing that has stayed the same is the fact that open source is the key to our business model. And the reason is that we provide open source services, transformative services that help people adopt new workflows and design methodologies to build better next generation systems. We also use those methodologies to implement next generation systems for our customers. And we call those systems software driven because even though we do a lot of like hardware FPGA stuff, we believe that taking a software approach to them, just like James was talking about and his background is implying, is a good idea. There's a lot of great lessons to be learned in how open source transformed software to be transformed and transported into the hardware space. So what we help people build is anything ranging from autonomous vehicles to satellites, through security, all sorts of industrial equipment, medical, laboratory equipment, and so on. And we do hardware, software, AI, FPGA and ASIC is what I'm going to talk about today, and also tools that kind of empower all the other segments. So we don't just build like the current state-of-the-art things. We also think about what's going to come after and how we can use open source to improve the next level of development. If you're really curious about what we do, like on a more practical level, you can take a look at the technology showcase on our main page. There you'll see a lot of projects that we're involved with, and they'll range from boards to software operating systems, different kinds of IPs, different kinds of proof of concepts, and so on. Be sure to check that out. Each of those is a blog note that describes the thing, and very often leads to a GitHub repository that holds the stuff because we publish what we do quite extensively. Now, to the ecosystem part, there's a bunch of organizations that we take part in, and these are Linux Foundation, Zephyr Project, Chips Alliance, RISC-V, and of course, OpenPower. I like that James actually mentioned, I think, all of them. in his presentation. And we typically try to play the strategic and kind of ecosystem role in those organizations. So we adopt technologies that they build early. We help, of course, build them. And we try to see what are the synergies and how we can connect those ecosystems. We believe that there's a lot of value to be had in this collaboration between hardware and software divide, and between groups from various industries, because sometimes they just don't see the low-hanging fruit that's just a neighboring field. And we say that, open source is very meritocratic. So, the best technology wins, or actually it's typically not just one, it's a multitude of technologies. It's a connected network of technologies that wins. And so we don't view those things like RISC-V and OpenPower, we don't really view them as conflicting in any way or competing. We believe that there's space to build things and collaborate. And we say that open source lifts all boats, because if you really create open source IP, if there's real open source collaterals coming out of an organization, it just becomes very easy to build on top of other people's work and reuse, repurpose stuff, combine and rehash things. And we've seen that already. A lot of the work we've done for the RISC-V Foundation is immediately useful, in OpenPower and vice versa. There's a lot of technological transfer that can happen between all those orgs. And why we joined OpenPower as such. So the story is we'd actually worked with the Power ISA some years ago in the automotive context. We even had support for that in the early version of what was to become Keynote. But over time, as our focus switched more and more into open source, also in hardware, we kind of focused on RISC-V, which was the first major ISA to open source itself. And actually, OpenPower is kind of coming to this stage and like making open source, put it really front and central back on our radar, and also our customers. There's some great enthusiasm that OpenPower managed to build around the microwatt and the initial releases. And of course, this momentum continues now with some great and exciting things being announced today. So we feel it was really a good moment to join. And also because cloud and data center are coming increasingly more into our focus. We started out from edge devices, but actually today we cover, all sorts of like cloud-based systems, continuous integration, big deployments, and so on. So cloud and data center have become pretty important for us. And with microwatt and similar things, OpenPower has also been showing that it's not just about data center, it's also about the other things. So I think we've just gone closer together. I really like this trend. So we joined in May, and we also added support for the Power ISA and Keynote. I mean, we added it back in a sense, and microwatt was our first target. I think the most important job that we'll have to do here is really connecting Power to this open source ASIC and FPGA ecosystem. I mean, this already has been happening, of course, but we can actually provide services and help for people to adopt all those great things that are being done and improve them also from the Power point of view and around the topics that Power cares about. There's some challenges that kind of the ecosystem is facing that I think open source is helping fix. This slide is from the CHIPS Alliance presentation. We're having a summit 2 days from now where we'll be discussing all sorts of challenges like this and how to fix them, and OpenPower is part of that story. But the story is broader than that. The story is all about kind of how do you do open source digital and analog design of chips and FPGAs. And the challenges are that there's significant costs with latest gen technologies. There's a lot of technology that's being kind of stalled and innovation that's being stifled because organizations are pretty old and awkward and don't collaborate much in this space. And also there's a need to build more purpose-built stuff, but at the same time, this need also generates the fear of fragmentation. So open source becomes the solution to all three of those problems, because in the cost space, you can just collaborate to share the costs. And I'll show you a few examples later on in this presentation. For innovation, I think it's especially important. I mean, open source has allowed us and other people to benefit from this incredible energy where people just start collaborating, on GitHub without really having to ask for permissions. And without signing NDAs, without like royalties and license fees. And we'd really seen some incredible spontaneous activity that just happened I mean, there's always a reason, of course, but there's some kind of common interest and so on. But if you have proprietary stuff in place, very seldom does this common interest actually transform into real technical work. Whereas in open source, it just becomes very easy to jump on a train and start working together. And the purpose-built stuff, like if you have a methodology that's based on open source, even if the end result is kind of very specialized, very often you can find common elements, and open source allows you to do that much more effectively. In contrast, if you have proprietary tools, very often, you know, each and every vendor, each and every type of application has their own little quirky tool chain and flow that is very hard to reuse. So we think that kind of the need to build a lot of disparate things is solvable by having common tools in place. So what I call this journey is a long but hopeful journey towards open source. So of course, it's going to take a while to make all of this open source. But on the other hand, there's a lot of hope. There's a lot of bright spots and great examples of things we've already been able to accomplish. So bear with me and I'll try to tell you about some of them. I think the first up and kind of really deserving a lot of attention is the Skywater PDK. It's the first open source manufacturable PDK out there. It's a 130 nanometer process design kit, and it can be used to make some practical stuff. Of course, if you're used to taping out 5 nanometer chips, then perhaps it's not so much fun for you yet. But of course, this is just the beginning. This is just the first of a kind. And it's a very important milestone because nobody had actually achieved that before. It's a collaboration between Google and Skywater primarily, but also Fabless, Blue Cheetah, and Antmicro, a big number of academic partners, and Chips Alliance. You know, it's kind of important in itself as an open source collateral, but like what's even cooler is that there's a free shuttle run paid for by Google that's associated with this PDK, where you can actually get your chip taped out in this process, assuming that the chip is open source and you comply to some of the rules that are kind of sketched for you in this project. But in reality, you know, the rules are pretty lax. It's supposed to be innovative. It's supposed to be creative. It's supposed to open up chip design to groups that might have not like necessarily done chips before, or at least wouldn't have done a chip in this context normally. So really, you should be excited about the Skywater PDK. And there's, you know, if you're not excited about 130 nanometer, think that this is just the first step. We're going to go to 90 and 45 nanometer at some point. And if you've been looking at the A2I GitHub repository, you might see that 45 nanometer is already in the A2I territory, right? So you can see that even though this generation isn't really ready to build things like, you know, OpenPower is releasing, at least on the high end, at some point, we're actually going to be able to do this. And all of this is going to be open source to the metal, as we say. And as a nice kind of cherry on top, there's a t-shirt giveaway for people that kind of contribute to the project and build things. There's 2 types, actually. One of them is for contributors, when you actually like improve Skywater PDK, and you can do this. Another is for fans. I have the fan t-shirt with me today. I can show you. So that's what it looks like. I hope it's visible. That's the backside. So if you want to get one of those, just kind of get involved with us and start working on the Skywater PDK, or just become a fan, and you know we might be able to give you a T-shirt at some future event. The T-shirt was prepared by Antmicro and Google, and if you want to contribute, just look at our guidelines. We need a lot of help, and especially you should see the incredibly popular talk by Tim Ansel from Google from the FOSSI dial-up in June, I believe. There's a link here. And that talk is a very long, deep technical dive into Skywater PDK. So I'm not going to talk about this anymore today. Complementing the Skywater PDK in a sense is Open Road. That's another EDA-focused program. That's actually part of the DARPA IDEA program. And this is part of Chips Alliance. There's a talk about this on Thursday. And Open Road is concerned with building a fully open source and automated digital design flow. We want to have, you know, no human in the loop build flow. We want to replace humans by machine learning. We want to have very quick turnaround and enable like critical innovation without having to care about this entire framework, right? The framework should be in place and people should be able to innovate on parts of it. And the goal is full like RTL to GDS designs It's really incredible. And if you combine that with Scouter PDK, the name for that is OpenLane, and you can actually build stuff with this flow. More information can be found on GitHub, of course, but this is one of the more exciting projects of CHIPS Alliance. Now, when it comes to tools, of course, they're very important, but sometimes it's as trivial as kind of not having support for the language that you use. System Verilog has been this historical thing that wasn't really well supported in open source designs and tools. So this is no longer such a big problem. Google has released one parser called Variable. It's a full-fledged System Verilog parser that's used at Google in the OpenTitan project and RISC-V and some other projects too. And we've done quite a lot of development work for it. Of course, Google is still kind of developing and maintaining it. And we'd also integrated that with other tools like FuseSock, which I'll describe in a second. You can do linting and formatting of System Verilog code easily with that. And we have a blog note that describes this process. So you can go and take a look on our blog. Kind of even more to the point, for System Verilog, there's a framework called Surelog and UHDM. And Surelog is yet another like parser, but also preprocessor and compiler for System Verilog, including not just not just for linting and formatting, but actually for other purposes too. We want to use Surelog and UHDM as this kind of interop layer, and we want to enable connecting different fronts and backends together in a very modular fashion. And this is developed in collaboration between Google and Antmicro. And so we'll be able to use that for various open source tools. We're already kind of using this, but of course the plan is to make it even more of a standard. And you can see a diagram here, that's our target. We want to have a single parsing framework for things like Yosys, Verilator, Icarus, and other simulators. And the input languages might in the future be like, today we're focusing on System Verilog because that's not supported well, but you can imagine plugging in different languages like VHDL. Another project that Antmicro is participating in and CHIPS Alliance is kind of pushing forward is implementing Verilator support for UVM and other types of Verilator improvements, but this is the single biggest effort. If you don't know Verilator, you should. It's a very cool, fast simulator that outperforms many proprietary alternatives. It's really developing fast now with somewhere from Wilson Snyder, the author, one of the original authors, the FOSSET community, and CHIPS Alliance. And we're spearheading that development, adding this UVM capability. It's a long way ahead of us, but we're making good progress. And in the System Verilog space, we know we're not just kind of blindly hacking things together. We actually have a System Verilog test suite in place that allows us to test a variety of open source tools against different kinds of System Verilog designs. Of course, there's a bunch of RISC-V cores. There's a bunch of other kinds of designs. There's a huge test suite for the entire System Verilog language spec. So I encourage you to go and take a look at this test suite. That's what it looks like in a bigger zoom. You can see a bunch of tests on the left, a bunch of tools on top. Okay, so going on to a more like IP-oriented part, I wanted to highlight LIDEX, which is a really cool ecosystem of IPs, mostly for FPGAs, but actually we're also thinking about it in the ASIC context, and I'll tell you a little bit about that in a second. As you can see, there's a huge amount of IPs there. There's a lot of great things you can build with LIDEX, and actually Microwatt has been integrated with LIDEX, leveraging some of those IPs there. There's a lot of CPU options, of course, including Microwatt, but the great thing about this framework is that it allows you to build all sorts of frameworks that are very modular. And it's also the important thing to know, this is very well supported in things like Zephyr and Linux and simulators like Renode and Verilator, and also open source FPGA tools like SimiFlow, so that if you kind of use LIDEX, which we encourage and we kind of implement that for a lot of customers, you'll get a very portable framework to do things in. So go ahead and check it out. And one thing that needs particular mention here is an open source DRAM controller that we're developing. It's actually the best in class, open source DDR3 and 4 DRAM controller for FPGAs. And a lot of development is going into it right now, both from Antmicro and its creator, Florent Kermarek. And currently, we're also working on making this capable of, being built in an ASIC. Again, some way ahead of us to get that, but it's definitely a worthwhile endeavor. And also excited our plans to use Light DRAM as an experimentation platform for research into DRAM in general. Yeah, I encourage you to take a look at Light DRAM. It's a really great example of an open source IP that's really enabling a lot of different ideas and use cases. Renode is Antmicro's framework actually for simulation. So we're going somewhere in between, a hardware and software development and possibly FPGAs. I explain in a second. Renode lets you rapidly create different kinds of software, and you can debug and test things very easily. And the important thing to know is that you can simulate not just like a CPU, but also sensors and IPs and different kinds of protocols and networking mediums. So you can really test real-world systems. And it's been used for things like porting operating systems, doing CI, machine learning testing, and benchmarking. I'm going to tell you a little bit about this in a second. And also, for example, hardware software code development. And the next slide is about that. So a lot of people have actually used Renode in a context that initially we didn't really kind of pay a lot of attention to, but increasingly is becoming a very important use case. First of all, we have the ability to co-simulate stuff with very later and physical hardware, which gives us the ability to kind of simulate some things fast, because Renode is an instruction set fast simulator, and some things kind of in more detail because we might not have a simulation model for it. And since we have a lot of configuration capabilities and we can extend using plugins, it becomes very easy to like prototype things and just quicker to build things in Renode than otherwise. We have some examples from our customers where they could build things much faster with Renode than they could in HDL. So they actually ended up prototyping Renode, and then when they found the right mix, they would go back to HDL and do the rest of the work. We can do execution hooks and fine-grained control of execution, and we can do custom instructions as hooks and plugins, so it's really extendable. And of course, it supports LiDX and OpenPower, so it's a good starting point for your development on Power. And the thing that Renode allows you to do is writing tests in a Pythonic framework called Robot. Actually, you can do other types of test frameworks too, but this is the one we support pretty well. We can generate very fancy reports. Of course, this one is, everything passed, but the one where things don't pass is more red. And then we can also build like whole dashboards of various kinds of binaries and demos that we test. So this is a dashboard that we're working in, a public dashboards of different firmwares that we're testing in Renode, and we'll be publishing some collaterals like binaries that we know are working in Renode. And if you want to really kind of try out Renode quickly, just go to Colab to this link, and you can actually run it in the cloud because it's very easy to install. So you can probably, if you take a look at the screenshot, you'll see that's what you need to do to install it on a vanilla machine. And then you can actually run a TensorFlow Lite pipeline with some machine learning stuff in the cloud, completely in the cloud without hardware. It's pretty exciting. It's a collaboration with Google and other parties. I must say, this is really developing very nicely. It's kind of showcasing how Renode enables great stuff. Moving on directly to FPGAs now, I wanted to highlight SymbiFlow, which is a fully open source FPGA toolchain, and it's really making rapid strides. I think the one thing that needs a shout out is QuickLogic's participation. These guys did the first vendor-supported toolchain, so they actually kind of paid us to develop a toolchain for them, and this really kind of helps to get a leading position in the space. And since QuickLogic actually sells eFPGA, right, you can buy the FPGA fabric from them, which will be supported in open source tools. Like, you could be building your next generation chip with some FPGA capabilities supported by open source tooling, supported by the vendor, which is, like, again, a historical first. Really great guys. We've done a lot of work with them also for Renode and Zephyr and other things. They've really gone all in on the open source mentality, and we kind of encourage other people to do so too. And what SymbiFlow does, it makes FPGA development much more software centric and collaborative, and especially for research and prototyping. Like, even if you're not really into FPGA, but you're doing ASICs, this is really important for you, because if you want to kind of rapidly prototype ASIC stuff, you're going to use FPGAs anyway, and SymbiFlow is kind of made for that. We have already some good results for some niche applications which are not supported by the vendor toolchains. And we plan to make FPGAs more mundane. Like, you have GCC for code. We want to be the GCC for code where you don't think about compiling things, you just compile them. And we want to make FPGAs part of future SoCs without hassle. Go to SimFlow GitHub.io and take a look. We have a pretty fancy website. That's what it looked like. And that's also the support for different families right now. There's Xilinx, there's Lattice, there's QuickLogic. There's, of course, unofficial support for other things too. There's in-progress support for a lot of devices, but these ones are kind of pretty well supported. If you recognize some of these boards out there, then there's a high chance you can actually use SimFlow today. Okay, and SimFlow can also do VHDL now. You can use a plugin that kind of runs through GHDL. That's how you do that. And yeah, you can get a design from VHDL too, because our primary focus is Verilog normally, but there's no reason why VHDL should not be possible. Moving on towards the end of this part, there's also little tools that really help you out. FuseSock and Edelweiss are two tools made up by Olaf Kingren that help you like to create and reuse FPGA designs. You can reuse cores, you can create some kind of runtime configurations, compile configurations, you can port things very easily, you can let people reuse your code and set up CI very easily. And I'll show you in a second how you use Edelweiss to actually do that very well. These kind of little tools out there really help to pull the ecosystem together and increase reuse. And FuseSock has been adopted very widely by the community, and we help achieve that as well. We kind of contribute to it regularly. And the flow is kind of portrayed in this picture where you have a core library that fetches stuff from storage. It might be on GitHub, might be on GitLab, might be some local repository. You tell it to run a kind of a simulation, for example, and the manager just fetches the right cores with the right order and right dependencies. And then Edelweiss just goes and transforms this into a specific project for a specific tool, which might be a very later simulation or, Quartus synthesis and place and route. We also have a tool for measuring performance of FPGAs. It's a tool by Antmicro to kind of show how your designs progress over time, whether you're getting better or worse. We have nice facilities to measure, resources usage and runtime and so on. It uses Edelweiss, so it's a nice illustration of how Edelweiss is very useful, part of SimFlow suite, and I also encourage you to try it out. Okay, summarizing. Hopefully I've been able to show you that there's a lot of progress. So I would say that the outlook is very sunny, but then again, you should bring a developer just in case, in case it rains and you have to fix things up. Definitely we have incredible progress, but there's a lot of legacy. There's a lot of legacy we're fighting. There's a lot of mentality problems also, a lot of kind of things that are secret just because, not because there's a reason. And so far, we've been very successful. We've actually managed to reach as far as the PDK. So I'm joking that the Skywater is the limit. And I think that power could really play a vital role in this ecosystem, because if it aligns well with those efforts, if it kind of learns how to benefit from all those rapid developments and this collaboration, I think that power, with its established brand, its established ecosystem, and its kind of good support in the server space, is a really valuable player. And that's what we want to enable. That's what we want to provide services for. That's kind of how we envision OpenPower kind of leveraging this ecosystem. And the last thing I wanted to say is to invite you over to the Chips Alliance workshop. This is taking place on Thursday, and I'm going to have a talk about enabling fully open source and continuous integration-driven flows in ASIC and FPGA development, which will present the progress of the tools working group. It'll be a little bit more technical, but of course a bit similar to this one. And I encourage you to join, because there's a lot of awesome speakers, including some OpenPower Foundation members like Google or UC Berkeley. And there's also what I mentioned before, talks about OpenRoad and SimpliFlow. Hopefully I got you interested in those projects, so you'll come and listen to those talks and learn more. Check out the schedule for more. And yeah, I invite you to the Chips Alliance workshop later. But today, of course, I invite you to see all the exciting stuff that the OpenPower Foundation has prepared for this event. I'm really dying to see this. Thank you very much. Thanks for your attention.
Thank you, Michael. And now for our next keynote speaker, Allan Cantle. He's the CEO of Nalisway and the new technical director of the OpenCAPI consortium.
Hi everyone, I'm going to talk to you today about OpenCAPI. I plan to give you a better understanding of the reason for needing a new memory fabric, and then highlight OpenCAPI's strengths for a pure data-centric world. So let's start with the basics. We all recognize this CPU-centric architecture, so much so it's a generational religion. We have the memory bus, which is latency critical and bandwidth critical, the processor interconnect buses that are all proprietary, that are latency critical and bandwidth critical. Then we have storage attached, which is more latency tolerant and bandwidth tolerant. And finally, we have the network attached, which is frequently latency relaxed and bandwidth critical. So essentially, we've got, as an analogy, the internal combustion engine car is a very similar thing. It's been around for decades, and it's really it is great at what it does, and often you don't need to change it. However, we've seen this data-centric shift going on over the last 15 years or so, where we've got memory in a CPU-centric world. What I mean by that is, well, essentially the interconnect bus is a coherent memory interconnect to start with. We're seeing that storage is becoming persistent memory, more so as we go forward. And we're even seeing that we're remotely connecting memory over the network. So a better way to represent this would be these different buses just connecting to memory. In a way, this blend of this data-centric and CPU-centric world is a bit like a hybrid electric gas car, such as the Toyota Prius. And let's face it, the Prius has been around for 20 years. It made a lot of sense. It's a good way to evolve from one world to the next. But we shouldn't forget that there are several compromises that we have to put up with. We have complex logic translations going on between all these different buses. And it's really a wasteful use of the I/O resources on the processors. And not only that, if we look at the cost of our data-centric servers these days, we find we're spending the vast majority of the money on the memory infrastructure and very little, relatively speaking, on the processor. So really, we're getting to a situation where the tail is wagging the dog. So ideally, we'd like to converge these memories and put them all together into a tiered memory infrastructure on one new memory bus. And we need to get the best of all the performance we need is the lowest possible latency still, high bandwidth, and really scalable. And we shouldn't forget that the memory is not existent in a single point. It is certainly a data plane continuum. 1 nanosecond per foot to 134 milliseconds for light to travel around the world. So we need to take this into account in our system, in our data-centric world. But what about the PCI bus? It's a peripheral component interconnect. We're increasingly seeing peripherals being absorbed into the CPU, and that becoming more of an SoC device. And really, even the Ethernet now is becoming directly coupled into the processor. So we're looking at a systems on a chip CPU rather than purely just a CPU. And the PCI is becoming a legacy bus, which is all very well. But one thing we shouldn't do is we shouldn't compromise our new memory bus. It's latency critical memory bus with unnecessary legacy support. We really need to keep that clean. So pulling that all together, we get this data-centric core building block, a really clean slate when we really look at data-centric purely and don't worry about legacy. A bit like an electric car, it looks really pure. And OpenCAPI is that new memory bus. It offers this lowest possible latency, high bandwidth, and it's very scalable. So, but what about other processors, accelerators? We've got peer processors. I tend to call them peer processors or SoC variants. They come in the different flavors, CPU and GPU, and FPGA and AI. Really, you can categorize them into two separate categories: latency critical, really von Neumann processors, and you've got to get over that von Neumann bottleneck, and hence the coherence critical part of this. And then the AI and FPGA are more latency relaxed streaming processors, and they're often used for data reduction filtering functions. And coherence is frequently unnecessary unless you've got a tightly coupled accelerator, so a CPU trying to accelerate a single thread. So putting that all together, we end up with a distributed memory data plane and all the different processors attached to it. So really we've got a heterogeneous distributed computing going on here. And we can see this really at the rack scale or all the way up to the data center scale, and it would look something like this. But we can now see that this is truly data centric in our thinking of how to represent this. And increasingly, if we look at the buzzwords around, we've got the cloud, the edge, and the intelligent IoT, Internet of Things. And I've just highlighted here that often with so much data coming from the IoT, like CCTV cameras, etc., you often want to just filter out the information that you need and only offer that to your data plane continuum, like maybe extracting faces from video or number plates, etc., rather than sending all of the video into your memory structures. And that's often driven by the comms bandwidths available or the cost management that you've got. So really we're talking about a generic system level domain specific architecture here. And this is an area that I specialize in with my consulting company, Nalisway. So here, this is really the core building block we should think of as we go forward with computing. So great concept, but the reality? Well, the reality is that OpenCAPI is a production-ready memory fabric today. OpenCAPI is the third generation that was deployed in 2014. The OpenPower initiative focused on data-centric open community innovation right from the very start. So we've been looking at the pure data-centric approach all the way back then. This is not just a spec that's yet to be finalized. We've had a lot of work in progress, a lot of learning, a good few mistakes on the way, and but we're here today with a really effective bus, and it's showing lots of promise. The OpenCAPI PHY is fundamentally an 8 transceiver lane bus with a few sideband signals. 25 gigabits per second has been in production since 2018 and introduced with Power 9. And it's it's the only bus that's highly focused on the lowest possible latency in point-to-point interconnect. OpenCAPI is also introduced this open memory interface, OMI differential DIMMs, that were introduced in 2019. And in my view, this is a game changer piece of the OpenCAPI infrastructure. So putting that pictorially, what's in production today, the Power 9 and the Xilinx FPGAs, and we've got this OpenCAPI interconnect and the memory sharing going on here. Additionally, there's been a lot of work going on in the FPGAs called Open Acceleration Framework, OCXL, which really brings the OpenCAPI framework in the FPGA to connect memory and external networks into it, and also make it much more easy to program your FPGA with your application in C or HDL. And on the software side, we've got the software stack, including Python support. I should say that the OCXL, there's a presentation at 10:35 a.m. Central Time on track 2A to give you more details on this. And then we've got the DDIMM, the OMI DDIMM. Microchip actually made a buffer chip, and that's got less than 10 nanoseconds latency adder over a standard RDIMM. In terms of keeping that memory channel as efficient as possible for the processors. And today we can actually connect these OMI DDIMMs into the FPGA fabric to really amplify the memory bandwidth of the FPGA fabric. And to that end, Oscar Menzer from Maxeller will be giving a lightning talk on FPGA application acceleration of memory bound problems with OMI. It's going to be at the Birds of a Feather panel session at 1:20 p.m. Central Time today on track 2A again. The key thing to take away here is all of this I've just talked about is all the RTL in the software is proven and fully open sourced. So looking a bit more into the hardware, the Power 9 systems that support OpenCAPI free include the IBM AC922 platform, which was #1 and #2 in the top 500 supercomputers for the last few years until recently. And then we've got the IC922 for bringing in storage dense servers and AI production, which also supports the OpenCAPI free. So we've got some good server level products supporting the OpenCAPI environment. On the FPGA accelerator front, we've got a multitude of offerings from Alpha Data and Bitware, focusing on all acceleration use cases. Bitware's is more focused around the storage of different medias and attaching them to OpenCAPI to bring the different medias in from ZNAND and NAND devices. Whereas Alpha Data's is focusing more on the larger FPGAs, which also include the HBM memory on package. And I'm delighted to say that Craig Petrie from Bitware will be giving a lightning talk at the Birds of a Feather panel session at 1:20 Central again on track 2A. So I encourage you to come along to that. So with all of that infrastructure we've got for quite a while now, we've got quite a few success stories here, and I won't go into them in details. If you look in the agenda, you will see these different tracks, which will give you some good examples of what you can do with this OpenCAPI framework. Going back to the OpenCAPI memory interface in a little bit more detail, really what we're trying to do with OMI is we're trying to herd the divergent memory choices, because now everything can be treated as memory and we're wanting to increasingly treat it as memory, and so therefore we have to commonize these interconnects. The trades between these, which ones you choose for your system, are quite a multitude: depth versus latency versus bandwidth versus persistence versus power versus cost. And depending on which one you choose, you'll get a different balance of those factors. They all have their own unique interfaces. Not one of them is really compatible with the other. And so OMI is really trying to normalize those memory interfaces. And for now, whilst we can use no OMI memory buffer for these different interfaces, and that's what we're doing. So obviously the DDR4 OMI DDIMM is the critical one to get in place, and the latency is pretty damn fundamental on that one. And that's available today from Smart Modular, Samsung and Micron. And Bitware's 250 HMS has given us access to low latency NAND on the OpenCAPI bus. And Bitware's 250 SoC is also giving us access on the OpenCAPI bus to NAND via NVMe storage. So we've covered a good few of the bases here. And also, if that with the emerging memory that's coming out, there is an opportunity for these companies to actually support natively OMI on their devices, which will be a nice change moving forward. So, but why OMI? What is the OMI advantage over other approaches? One is it exists in production today, so that's a pretty compelling one. But the key thing here is you're getting memory bandwidth and depth at low cost. And so the way I'm showing this is the Power 10 die, and I'm representing it by how much you can get, how much memory bandwidth you can get on the I/O edge. So there's 8 OMI interface PHYs on the left edge and 8 on the right, and it takes up 12.7 millimeters of the die. This is all to scale that I'm going to show you, and they're all based on 7 nanometer process nodes. The AMD EPIC Rome I/O die has DDR4 memory channels at either end, and so it has 4 memory channels at one end, and you can see it's slightly bigger edge area for those 4 channels compared to the 8 OMI channels. Similarly, on the NVIDIA Ampere device, it's got 6 HBM 2 channels, and 1 HBM is slightly smaller than the 8 OMI 5 channels on the Power 10, again 7 nanometers. But to really compare these, we need to look at the gigabytes per second of those channels. So 4 DDR4s is about 100 gigabytes per second on the EPYC. We're getting 400 gigabytes per second out of the 8 OMI DDIMM channels, and we're getting 311 gigabytes per second out of the HBM2 channel. So when we look at it as a gigabyte per second per millimeter parameter of edge die, you can see that OpenCAPI really does, the OMI really does win on all categories, significantly bandwidth-wise over DDR4, and surprisingly faster than the HBM2, which is really quite a surprise. And when it comes to depth, there is just no contest. With DRAM, the Power 9 is more than 2x of DDR4, and compared to the HBM, it's significantly greater because you're limited in capacity because it's on package memory. And OMI goes even further with different media types other than DDR4, like the 250 HMS. You can get to 1.9 terabytes per millimeter or greater. So this really is as compelling as it gets. In my entire career, I've not seen anything more compelling, and it's in production today. So it really is a no-brainer to adopt this technology. So we're not talking, this is no concept, this is reality. OpenCAPI is connecting the memory data plane continuum, and we can see it with Power 9 and soon to come Power 10, and the Xilinx UltraScale FPGAs and the Versa ones coming down the pipe. So really, I call to action here, put your processor here or your memory here in this fabric. This is definitely the best way to go if you want to shine with the technology you're offering. And remember, all the OpenCAPI and OMI RTL and software is proven and open sourced. So our journey though is still just really beginning. Please join the OpenCAPI and contribute back into our community. In summary, we do have this hybrid world that we've come from. It's been around for 15 years. Hybrids are not going to well on the electric on the hybrid car front. And so maybe we've got a few more years left in this approach. But one thing's for sure is the purity of the data-centric approach is really a no-brainer for high-performance computing applications today. An absolute no-brainer. And the only thing I'd ask you to take away is whichever camp you sit in, the hybrid camp or the pure camp of data-centric computing, really look at your problems, consider this data-centric template for your next domain-specific architecture. And if you look at your problem from this light, you will be able to come to the correct conclusions as to what is the best way to build your computing architectures. So thank you very much. May I encourage you all to come along to the Birds of a Feather panel session that I will be chairing at 1:20 Central Time and Track 2A. Thank you again.
Thank you, Allan. And now for our last keynote speaker, Mendy Furmanek. She is the Director of Power Open Hardware Business Development and the President of the OpenPower Foundation. And she'll be showing a quick video on IBM. So please welcome Mendy.
IBM Power. Beginning as an IBM research project in the 1970s, IBM Power CPUs have been helping organizations of all sizes innovate for decades.
Reduced instruction set computing, or RISC, pioneered by IBM. Improved now with a second generation of RISC. The Power Architecture. Performance optimization with enhanced RISC.
We believed we were making a more advanced RISC machine, and we did whatever we thought was necessary to get the best possible cost performance.
Gary Kasparov has resigned the position. It is stunning development.
Watson.
What is executor?
Right.
Same category, 1600.
Answer. There you go.
IBM Power-based CPUs can be found in the smartest AI supercomputers in the world, game consoles, and throughout the solar system in satellites and in planetary rovers on Mars. But power has been especially pivotal for enterprises. 80% of the US's highest revenue companies use IBM Power for their mission-critical IT applications. Many of the world's largest banks, retailers, and healthcare systems literally rely on IBM Power to power their business. Now, Power brings its legacy of innovation to the hybrid cloud with the launch of IBM Power 10. Designed over 5 years with hundreds of new and pending patents, IBM Power 10 is built to meet the needs of enterprise cloud computing environments that demand security, reliability, and performance. But what makes IBM Power 10 unique from its predecessors? First, energy efficiency. IBM Power 10 is IBM's first 7-nanometer processor, and it delivers 3 times greater energy efficiency and capacity, allowing for greater performance and more work. Second, scalability. IBM has made memory more available in the cloud with a significant breakthrough in IBM Power 10 called Memory Inception. This all sounds very sci-fi, but essentially, this clusters physical memory across a pool of systems, where any of the systems in the pool can access the entire pooled memory, up to multi-petabyte memory clusters. This allows for businesses to reduce their costs on the cloud for memory-intensive workloads. Third, AI. With AI improvements to its CPU cores, IBM Power 10 delivers up to 20 times better performance for AI inference workloads than IBM Power 9, meaning it can take previously trained AI models and deduce new information up to 20 times faster than IBM Power 9. This brings greater infusion of AI workloads into typical enterprise workloads on the hybrid cloud. And last but not least, security. In today's world of cyber threats, your data needs to be secure wherever it resides. IBM Power 10 has 4 times as many encryption engines as IBM Power 9, keeping your data safe in the hybrid cloud. Over decades, IBM Power has been elemental and vital to shifting technology trends. And as the world has changed and moved to the cloud, Power 10 underscores IBM's belief in the 4th platform of IT, hybrid cloud. With co-optimized hardware and software, IBM Power 10-based servers will deliver the future of the hybrid cloud.
Hi, this is Mendy Furmanek, and I'm very excited to be here as always with some new announcements for today. And that video was just showed about Power 10, because we're very excited about the fact that Power 10 has finally been revealed. It was revealed last month at Hot Chips. And you saw in that video some of the exciting news with respect to Power 10. But there will be a talk today going through the details of the Power 10 features. So I really invite you to join at track 1, 10 a.m. Central with Brian Tomko and Bill Starkey, the ones doing the presentation, but Jeff Stookley, another architect of P10, will be joining Brian for Q&A afterwards. Just on the features of Power 10, you see you got the data plane bandwidth, the capacity, the usability scale, just really unparalleled flexibility ranging from mission critical large scale to purpose-built systems to cloud data center. And you can see that through that video that the history of Power shows to just the broad spectrum of solutions Power over the 30-year decade history has been able to tackle. With this new Power 10 core, we've got the new core architecture, which we're super excited about because this is one of the architectures that was contributed to OpenPower with the opening of the ISA. They contributed the ISA that was used in Power 9, which was version 3.0C, but also for Power 10, they contributed the latest and greatest 3.1. And so there's going to be a talk about that as well on track 1 at 10:35 by Brian Tonto. There's right afterwards, there's another one at 11:10, which will be focused on a particular new feature on the MMA feature. So I really invite you to participate in those two sessions as well if you want to learn more about the compliancy features of the contributed architecture, as well as new feature function of version 3.1. This new architecture enables flexibility in the Power 10 chip. We have larger caches, reduced latencies. And then we have what we're known for, which is the end-to-end security, end-to-end all the time. And then energy efficiency. We're going to be 3x improvement over Power 9 for greener data centers for a cleaner planet. And then AI infused cores, supercharging the enterprise with AI inferencing. We're looking at 10 to 20x the Power 9 capability. Again, please come join the tracks. It's been a long road getting P10 out here, and we're super excited about it being revealed and for people to learn more about it and then what they can do in the open community with respect to the technology that it brings to the community. Next up is a new exciting announcement I get to make. So back in June, we announced the A2I core, which was in order core, and now we're announcing the follow-on, which is called the A2O core, which is an out-of-order version of the A2O core, or the A2 core. Sorry, it's designed to optimize for single-thread performance over throughput. So while it's a follow-on to the A2I, it really gives a different market segment that the capabilities of this core can go after. Example applications are artificial intelligence, autonomous driving, security, anything that really needs that single-thread performance over what the A2I core is for, which is high throughput. It still has that same balance, performance, and power with modular design. And then this one is in Verilog. So I kind of joke that it happens occasionally in IBM that we use Verilog. I think most people know we heavily use VHDL. And you'll saw that GHDL is starting to be more widely supported because we are putting things out in VHDL. But we do have the A2O core in Verilog. So we're excited about that. Please come hear the details at track 155 Central with Bill Flynn. The repository is open. It's out there on GitHub this morning. So the RTL documentation and the full FBA GA environment, just like we did with the A2I core. And again, it's got that actually interface you can use on the FPGA platform. So come hear the talk if you want to learn details. It'll be right after the details on the A2I, so you can come see both the A2I and the A2O core. Next up is another announcement, and usually I'm always talking about open hardware announcements, but this time I get to talk about an open software announcement. So we will also be announcing at this summit opening Power AI. So it's going to be under a new name called OpenCE, which stands for the Open Cognitive Environment. A little bit of the history of Power AI, it started in 2016 as a MLDL AI package proof of concept, and within a year, it was productized as Power AI. And it went on to create a larger suite of AI products. And then in 2019, it changed names to Watson Machine Learning Community Edition. And it went on to embrace kind of packaging and other architectures as well as part of that. And so now here we are in 2020, and we get to launch it open. And it's going to bring to the open community those scripts, frameworks, modeling, everything to package up, TensorFlow, PyTorch into a usable cognitive environment. If you want to hear more about this newly open run and governed midstream community project, it's on track 4 at 255 Central. James Kulina has been leading the space component of Power AI since 2016. We'll be talking along with Chris Sullivan from OSU. Oregon State University is an OpenPower partner, and they're going to take an active role in the community in putting out these binaries and getting the community to participate in pushing this project forward in the open ecosystem. It's a source-to-image project enabling improved consumability of AI and deep learning frameworks. And we're really excited to get it out there into the open community and see people coming in to participate, make it go even farther than it has in its short history of just 4 years. It's done so much to date, and we're looking at such a bright future going forward. The code's all out there on GitHub, so if you want to take a look early, you can go out there today, this morning, and get ready for the talk later today. Those are my announcements for today, and I'm really excited to hear everything else that the presenters have. We have 48 talks, a really packed schedule across 5 different tracks. So really excited to see everything that people are coming to the table to present, and also to continue forward and having a collaborative environment amongst the community, and more events that we can share what we're doing. Like James said, we're going to be trying to host more meetups and workshops and really keep us moving forward with that momentum as we progress forward with all our new initiatives. So thank you very much. I'm handing it back to James now.
All right, thank you, Mendy. Thank you to all our sponsors, Antmicro, IBM, OpenCAPI, as well as Yadro. This is great in terms of the announcements. Always welcoming these new innovations into the foundation, and I can't wait to see what all of you do with them. Just a quick note for today during the summit for discussion and Q&A. Please go to the schedule for every talk. You'll be able to find the Zoom link to that talk. And you'll also be able to find the Slack thread for the talk. So you'll be doing discussion and chat about the specific talk in the Slack thread. We actually have channels, Slack channels for each track, and then a thread dedicated to each talk. So please use the thread. You just have to reply to the thread, and it'll all categorize based on each talk. For the Q&A, Q&A will be handled within Zoom. So you'll be able to submit your questions in the Q&A button, where the speaker will be able to select it and read it out loud and then answer it. You'll also be able to, if there's multiple speakers, it's potential for one of the speakers to actually answer that your question in line, and then hand it off to the primary speaker to read it out loud or answer it. You can also raise your hand, and then the speaker can unmute you. You can answer or ask your question live. So there's a couple different ways to handle Q&A, but it will be handled within Zoom. So please leave all discussion and chat within the Slack channels and within each thread, so that we can easily navigate and see which ones you're talking about. But very excited for welcoming you all here, and can't wait to see all the great things you guys are doing. So thank you, and enjoy the summit.